Practical implementation and performance evaluation of vehicular communication. Vehicular communication is a unique type of wireless communication which was achievable because of the advancement of vehicular technologies and wireless communication. In vehicular communication, vehicles communicate with each other and with roadside infrastructures to share emergency traffic events, traffic details and road information collected by vehicles. There are multiple standards defined for vehicular communication in the world. Most of them share similar characteristics to ensure global compatibility. Vehicle manufacturers implement these standards in their vehicles, but the implementation is proprietary. IEEE 802.11p Wave standard is selected for this project, and the aim of this project is to provide an open-source implementation of the MAC and physical layer of Wave protocol and evaluate its requirements and performance. Even though there is previous literature available in this domain, they are mostly done using software simulations, where the real hardware performance of the protocol is not evaluated. This has motivated us to implement a hardware solution which supports IEEE 802.11p Wave and perform real-world testing. This project was completed in 3 main stages. First, vehicular network simulations were conducted to identify the ideal configuration values for hardware implementation parameters. Then the hardware implementation of the IEEE 802.11p Wave MAC and physical layers were done simultaneously in 2 separate substages. Finally, the implemented parts are integrated and the full system is tested and evaluated for performance. In the simulation stage, vehicular network simulations were performed to identify ideal configuration values for the hardware implementation parameters. Simulations were conducted using VANS framework, which is a combination of a Net++ network simulator and Sumo Road network simulator. The simulation parameters were selected based on the protocol specifications of the IEEE 802.11p Wave MAC and physical layers. The hardware implementation is done on a Basis 3 FPGA development board. It has a mid-range Xilinx Artix 7 FPGA chip. Xilinx Vivado high-level synthesis is used as the implementation technique. In this implementation, the MAC layer and the physical layer of the IEEE 802.11p Wave standard were implemented simultaneously. The 2 layers interact with each other using the service access primitive interface defined in the IEEE 802.11p Wave standard. This stage produces a combined MAC and physical layer design as an IP core that can be used as a module in a system design done in hardware description language. In the last stage, the final system design is created using VHDL, incorporating the IP core created in the previous stage. Xilinx Vivado is used to create the final design and integrate it with the Basis 3 board. Since the required radio module which supports 5.9 GHz bandwidth couldn't be found, implementation was tested using a wired UART connection with 2 Basis 3 FPGA devices, where one works as the transmitter and other as the receiver. 512 bytes of data stream is sent from the PC to the transmitter FPGA device, and it does the processing of the data and transmits those to the receiving FPGA via 2 PMOD UART channels, one for the I channel and other for the Q channel. Then the receiving FPGA does the processing of the data and sends it to the receiving PC. Vivado synthesis and simulation reports are used to evaluate resource usage and performance of the implementation. They show that the usage of the DSP units in the combined receiver and transmitter hardware design exceeds the available resource amount in the Artix 7 FPGA. Most of the resources have been allocated to IFFT and FFT units in the physical layer due to its complex calculations, and these units have the highest latencies out of all components. Performance of the implementation is measured using the data processing latency of the final design. The transmission and receiving devices record 16.17 and 15.7 milliseconds respectively for exchange 512 bytes of data. With the success of this implementation, this can be further extended into a product with both commercial and academic usage.